Okay, hi everybody. Welcome to our session on atmosphere, ocean, and climate dynamics. We've got six nice talks lined up for this session. Just a couple quick remarks before we get started. Every speaker is allocated 15 minutes. So the plan is we'll do a 12-minute presentation, leaving 3 minutes for questions. So I will give you a 2-minute warning. So that'll be at the 10-minute mark. So 2 minutes left of the 12 minutes allocated for talking. There's an opportunity to put questions in the chat for the audience. And I'll just ask other speakers when you're not speaking to keep your mics muted. And yeah, so our first speaker for today is Robert Fajber, and he's going to talk to us about tagging water in an idealized aquaplanet model. So go ahead, Robert, you can share your screen.
Okay, is that working?
Yeah, it's perfect. Thanks.
Okay, great. Well, thanks so much, everyone. Really excited to be here. Yeah, so today I'm going to talk about water tagging in an idealized model. So you can see this dice animation here. I'll explain what this is later, but basically we're trying to track water vapor from all the different source regions it has throughout the atmosphere. Okay, so why might you want to do this? Well, the basic reason is that we're interested in how water moves through the atmosphere for a whole variety of reasons. One is that this is useful for interpreting isotopic ratios. So if you have some paleoisotope record somewhere and you see some water in it, you'd like to know where that water came from, because really that water might only be indicative of its source region. It's also really important for analyzing remote teleconnections. So people like to talk about these remote SST anomalies we have and what effects those have on continental precipitation. But you'd like some way to kind of mechanistically link those SST anomalies and the extra water vapor they produce to actual precipitation events. And so that's another reason why you might want to track water vapor through the atmosphere. And the lastly is that often we're interested in local water vapor cycle feedbacks, things like recycling ratios. So actually the plots over here, these are export fractions. So this is kind of the opposite of recycling ratios. So the export fraction, basically if the export fraction is 1, that means that all the water vapor that's evaporated at that grid cell goes somewhere else before it precipitates. And if the export fraction, if the export fraction is 0, that means that all the water vapor is recycled over where it's evaporated. So you can see there's some areas where the export fraction is really small, where a lot of the water vapor is being recycled locally. And there's some areas where the export fraction is really large, where all the water vapor is being ejected somewhere else. And so people have been using this technique called water tagging to study the way the water flows through the atmosphere for a long time. But it's usually only been applied for realistic models, which can make it kind of difficult to do experiments with and understand. And so what I've done is I've basically taken the water tags and tried to put them into the most simplest model possible to study water vapor in. So I'll just run through this really quick. It's a hemispherically symmetric aquaplanet without any seasons. This is the ISCA model, if you're familiar with these idealized atmospheric models. It's a T85 resolution, and it has really simple parameterization. So it has radiation, but it's not very complicated. It has convection, boundary layer parameterizations, and it has a representation of ocean heat transport, where basically we just put in some artificial heat fluxes of the surface that kind of mimic the effects of subtropical heat transport. And just to show you that the model's not completely crazy, I've plotted some fields over here on the right. So you can see this is what the zonal mean temperature looks like. You can see the atmosphere. You get a Hadley cell in the tropics, and then a Ferrel cell in the mid-latitudes. You get a lot of tropical water vapor, just like in observations. And then the condensation, you can see that there's tropical convection in the deep tropics, where you have a lot of convection right over the equator. And then the mid-latitudes, you see that there's the secondary condensation maximum, and that's coming from the baroclinic eddies. So this is the model we're going to study. And just to briefly explain how these water tags work, basically the idea is that we'll take our surface and we'll divide it up into a whole bunch of different latitude bands. There's 8 of them, but I'm just showing a couple here. And basically over each latitude band, whenever we have evaporation, in addition to adding water vapor, we'll add some tag. And that tag will basically remember where that water vapor came from. So if we're in latitude band 1 and we have some evaporation, we'll tag that water vapor Q1. Then if we go over to latitude band 2, we have some new evaporation, we'll tag that water vapor Q2. And so now our air parcel that has some water vapor in it also has these water tags with it that remember where that water vapor came from. And so then when we have condensation, what we do is we assume that the condensation is proportionally removing tags. So if there's more water vapor from Q1, we'll remove more of Q1. And there's more water vapor from latitude band 2, we'll remove more of Q2. And so this is kind of making a well-mixed assumption that we use. And this is the idea of how the water tags work and how we can use them to track water vapor from all these different sources. Okay, so what I'm going to show here first is the vertically integrated picture. And so on the left, I'm just showing evaporation. And what I've done is I've taken the northern hemisphere and I've divided it up into 8 latitude bands so that each latitude band is equal area. So the bands in the tropics are smaller than the bands in the poles, but they all have the same area. And what you can see is that I'm basically dividing up the evaporation into sources for these different tags. So there's going to be a lot more evaporation and a lot more tropically tagged water than there is going to be polar water. Then on the right, what I'm showing is the vertically integrated total precipitable water. And I'm showing this on a log axis. So these lines all actually do add up to be the white line, but it just doesn't look like that because it's on a log axis. But what you can see is that there's a lot of water in the tropics, and most of it's coming from really local sources, so from these deep tropical sources. And then as you go out and you look at the poles, you can see that there's very little polar water. It's this tiny line. It's almost completely cut off here at the bottom. But you can see that actually a lot of the polar precipitable water we see actually comes from subtropical sources. So water vapor that's precipitating between roughly 22 and 35 degrees or so is actually making up a lot of the precipitable water that we see at the poles. So despite how far away it is, these subtropical moisture sources are really, really important throughout the whole atmosphere, and especially in the poles. So that was the vertically integrated picture. But when you look at the vertical structure of these things, it also becomes very interesting. So here I'm showing that animation I'm showing at the start. And now you probably start to understand what this animation is showing a bit more. So on the top, I'm showing vertical sections. And these are near the surface. These are all at around 850 hectopascals or so. And on the far left, this is showing water vapor that's originating near the northern hemisphere deep tropics, so kind of right off the equator. And you can see at the surface, this water vapor gets mostly confined to the tropics where it starts. There's some extrusions that are able to make it into the subtropics or even the mid-latitudes, but it's mostly kind of confined to the tropics. We can compare this with the mid-latitudes, and here we see that now the water vapor that's emitted in the mid-latitudes is able to mix very effectively all throughout the northern hemisphere surface. And you can see that a lot of the water vapor is able to make its way up into the poles, although some of it gets mixed subtropically as well. And you can see how the eddies are basically mixing up this water. And then if we take a look at the polar water, well, first off, we can see there's not very much of it, which makes sense because there's not a ton of evaporation in the poles because it's so cold. But then we can see that a lot of the water vapor actually gets mixed equatorwards. So a lot of the polar water, despite the fact that it's being created in the poles, it actually gets mixed equatorwards. And so this is near the surface, but the picture looks totally different if we look in the upper troposphere. So the second row here at the bottom, this is showing an upper tropospheric slice. I think I picked around 230 hectopascals or so. And you can see now almost all of the water in the upper troposphere is all coming from these tropical sources. So these mid-latitude sources and these polar sources, they're not able to really make it up to the upper troposphere. And instead, almost all of the water vapor is actually coming from the tropics. So this is really important because if you want to understand something like the water vapor feedback, if you're looking at the water vapor feedback near the surface, well, that could be local sources in the case of the tropics or the mid-latitudes. Or if you're looking at the poles, maybe that's like a subtropical or mid-latitude source. But if you're looking in the upper troposphere, where the water vapor feedback is really sensitive, all of that water is originally coming from the tropics. And so if we want to understand what's going on in the upper troposphere, we really need to understand what's going on in the tropics. And so this is just another view of this. Here, instead of showing cool animations, I'm showing less cool zonal mean plots. And so to start on the top, this is the total water vapor amount on a log scale again. And these are for our 3 tropical latitude bands. In the middle, this is the condensation coming from the water vapor from these 3 latitude bands. And on the bottom, this is the fraction of water vapor that came from those latitude bands. And so you can see a lot of the tropical water vapor, as I said, very important in the tropics, but also in the upper troposphere. If we take a look at the subtropical water vapor, now you can see a lot of it spreading out and mixing much more equatorwards. You can see a lot of it's condensing in the baroclinic eddies and causing condensation there. And especially this water vapor coming just polewards of 30 degrees, a lot of it's really important in the poles. I skipped ahead a little too far, but you can see the mid-latitude water vapor is doing something kind of similar to the subtropical water vapor. And finally, the polar water vapor is kind of interesting because it's not very much of it, but a lot of it mixes equatorwards. Okay, and so that's kind of basically what our setup looks like. Now I'm going to try to run through just a couple of the experiments we've done. So the first one I wanted to show quickly is just what happens if you remove ocean heat transport. And so if you do that, you'll warm up the tropics and cool down the extratropics. But the tag distribution doesn't change that much. You get you get less water vapor coming from some of these tropical sources, but the overall distribution is kind of similar.
Okay, that's a 2-minute warning.
Thanks. This is really different than if you add a zonal asymmetry. So here, this is showing the response of temperature and stream function if we were to put in a zonal asymmetry in the ocean heat transport, creating something like a Walker cell in the tropics. And now if we look at the response of the tags, we get a really big difference. So now the tropical water vapor is reducing a lot, and the subtropical water vapor is increasing quite a bit. And so this is something I still have to investigate more, but it seems like there's much more sensitivity to the distribution of these water tags to zonal asymmetries than there are to zonally symmetric perturbations. We can also try these other experiments where we do things like turn off subgrid scale convection. So in this model, the convection scheme is just relaxing towards something like a moist adiabat. So if we make that relaxation time really, really long, it's kind of the same as turning off convection. And if you do this, you see that you reduce tropical water vapor right where you have the most convection happening, but you increase the amount of water vapor coming from these other regions. So in other words, how we think about these regional partitionings of water vapor are going to be dependent on how much water vapor is coming from the subgrid scheme versus the grid scale scheme. And lastly, I'll just quickly show what happens if we double CO2. If you double CO2, you get this big increase in water vapor, and it's almost all coming from tropical and subtropical regions. I'll skip this because I just showed that on the previous slide. But so in conclusion, tropical and subtropical water vapor can travel these really long distances. And this is important for water vapor content, not only in the upper troposphere, lower stratosphere region, but also for polar water content. But these water vapor transport pathways are really sensitive to details and things like convection schemes and zonal asymmetries. And so if we look at results in water tags in one model, it might not be robust to these features. And we need to do more to understand how these transport pathways are sensitive to these different things. And so lastly, I'll just say I'm really interested in seasonal effects and more on these zonal asymmetries. And I'm also going to work with a student on calculating water vapor lifetime. So much more to come in the future. Thanks very much.
All right, thank you. There's a question in the chat. Maybe I'll just read it. The question is, how high is the upper troposphere? And is the lack of an upper tropospheric water vapor transport from outside the tropics related to tropopause height being higher in the tropics?
So the tropopause height, yeah. So the answer to the first question is, I think it's more that the tropopause height is higher in the tropics than the extratropics. And I think basically most of the extratropical water vapor is being advected vertically in the tropics and then kind of spreading out laterally once it reaches the upper troposphere. And actually a lot of probably the water vapor in the lower stratosphere is coming in through the tropics and the upper troposphere. In this model, the troposphere, or sorry, I should say the tropopause is a little bit lower in the extratropics than it is in observations. So if anything, we would expect to see probably less water vapor entering the extratropics in this model than we would in observations. I think actually probably the biggest difference in this model is that in the configuration I'm running it in now, there's no zonal asymmetries, and in particular, there's no stationary waves. And I suspect that a lot of the stationary wave dynamics are pretty important for helping kind of create big anomalies in the tropopause that are useful for letting water vapor in. The other thing too we're missing is any kind of like monsoon or any of the kind of deep convection associated with monsoon cycles, which in observations is also pretty important for ventilating the UTLS from the extratropics. I hope that answered the question.
Yeah, that's great. Okay, so thanks a lot. And I don't actually see how I can clap on Zoom, but anyway, nice. And thanks a lot for your talk. And we'll move to our second speaker. So Donald, do you want to share your screen? So our next speaker is Donald Lai, who is going to talk about backscatter in radiative-convective equilibrium. Go ahead.
Hi, my name is Donald. Today I would like to talk about my project on backscatter in radiative-convective equilibrium. So as this viscosity model are dissipative by design, so backscatter, which is the energy transfer from the subgroup scale to the resolve scale, is often found to be possible. In fact, the magnitude of backscatter is often found to be comparable to the magnitude of the dissipation. So in this project, I perform a priori analysis on this subfilter turbulence in a high resolution simulation. And this could help us to do like an investigation in the backscatter. So in this project, the high resolution simulation will be filtered down to a lower resolution through a box filter, a Gaussian filter, and a spectral cutoff filter. So this is the detail of the simulation. So this simulation is a RCE simulation. It is considered as a non-aggregated RCE simulation. I will talk about what I mean by non-aggregated later on. So the resolution of this simulation is 1 kilometer, and we will filter this simulation to 4 kilometer to perform the a priori analysis. So these are the detail of the RCE, and by a priori analysis, I actually mean the calculation of the subgroup energy transfer rate. So this is the definition of the transfer rate P. And in our project, the positive P means backscatter and negative means dissipation. This is because positive means the energy transfer into the add into the resolve flow, and dissipation is negative because it's just energy lost to the resolve flow. And so, as I said, this is a non-aggregated RCE simulation. The picture you could see here is the top of the atmosphere outgoing long wave radiation. So as we could see, pretty scattered at first. This is at hour 59, and then as the simulation goes hour by hour, we could see that it start aggregate, and then it would disaggregate again. Again, this is considered as a non-aggregated simulation in RC literature, and this is the time. This is the full. So the picture that I showed you previously is just within this around 100 hours here. So it's actually in the first peak, as we could see, there's still a lot of aggregation, disaggregation happening even within like one peak. So the variance of top of the atmosphere outgoing long wave radiation and the domain mean outgoing long wave radiation is often used to quantify aggregation. So as we could see in general, we could see that there is like 3 main aggregation periods. So, and then the stuff where we were looking at was in the first aggregation period. And again, this is time series of P separated into backscatter and dissipation. So, and in this plot, only the box filter is used. And this plot shows the result in the upper troposphere. So here we could see that the backscatter and the dissipation curve resembles the free aggregation period here. And then we could see that there is a lot of backscatter and there's a lot of dissipation, and it actually sums up to a smaller green curve here, which is this green curve is the net result of the backscatter and dissipation. So we perform another simulation at 4 kilometers to compare to the a priori study that we have. So as we could see, the green curve and the red curve is pretty similar. It actually means that the 4 kilometer simulation and the a priori study actually match up really well, but I mean the 4 kilometer simulation using a traditional eddy viscosity model, so it is just dissipative. As we could see, although the green curve is negative, it is the net result of a huge backscatter and a huge dissipation. So this is the same plot, except that now we're in the lower stratosphere. In the lower stratosphere, the story is a bit different now. So we could still get a huge backscatter and huge dissipation, and we still get the free peak here. But now the net result, the green curve, is actually positive. It means that in the lower stratosphere, it is actually more dissipation than backscatter right now. So as a result, the normal eddy viscosity scheme would not be able to generate this backscatter here. So this is the vertically average. So in order to do a deeper investigation, I actually separated the subfilter energy transfer rate into 6 different components, and the 6 components are defined this way. So the P here. So let's say if we are looking at P12, it means that I is equals to 1 and then J is equals to 2. So it's actually, if we're looking at P12, it means that it's just actually tau12 times S12 here. So get back to the plot. So this is the vertically average component of the subgrid energy transfer rate. So as we could see here, the first stuff looks pretty random. There's not like a defined region that we have like strong dissipation of backscatter. Next to a strong dissipation, there's always some backscatter. Also, as we expected, stronger dissipation and backscatter often happens in the region of lower outgoing long wave, with lower value of outgoing long wave radiation. It means that strong backscatter and dissipation only happens when there is a deeper convection. So it's actually harder to see here, but in the plot that I will not be showing in this presentation, we could actually see that the vertical component actually responsible for most of the circular energy transfer. So we couldn't see one reason is because of the climate too. So sorry for that. But in the next in here, this is in the lower stratosphere, and stuff is more obvious here. So as we could see that now P11, P22, P33, and P12, they both seems like there's nothing there because there isn't much happening. So most things are happening in the shear components. And then as we could see here, the shear components, which is in fully red here, also suggest that the backscatter is really strong in the lower stratosphere in this region, and most of them will come from the shear components. And in and in this, so in the previous plot, we were talking about the subfilter energy transfer rate when we are using a box filter. Here we added the Gaussian filter and the color filter for comparison. So as we could see, the blue and the red curve here, and the purple and orange curve here, they overlap on each other pretty well. So it means that the box filter and the Gaussian filter produce almost identical results. And then another thing is the color filter. The result from the color filter is significantly stronger than the box filter and the Gaussian filter. So yeah, so although the color filter is much stronger, actually the net result that it produces also looks pretty similar to the result from the box filter and the Gaussian filter, as we could see in this curve. Like, it's a bit hard to see because there's so many curves here, but we could see that the net result from the box filter, the Gaussian filter, and the color filter looks pretty similar down here, except at some regions here.
Okay, it's just a
So
2-minute warning, Donald. Yeah.
okay, so this is the same. This is the same plot from in the lower stratosphere. So again, similar result, but now that stuff, the net result of the spectral color filter is also positive right now. It indicates that it's back. There are still backscatter. So no matter which filter you use, you still get dissipative behavior in the upper troposphere and backscatter in the lower stratosphere. So we have performed a budget and in the kinetic energy spectra. So this is the formulation, and this is how it looks like. So because time constraint, I will skip over a little bit, but essentially here we could see that in the transfer this is the nonlinear energy transfer, and we could see that it's losing energy in the upper troposphere. It is losing energy in the mean flow, and then it is transferring to the smaller scale. So this is a direct energy transfer, and then here we could see that the energy in the lower stratosphere, you could see that the energy is going from the small scale to the mean flow. So it means that there is an inverse energy transfer. So this is more clear. This suggests that this is an inverse transfer, and this suggests that it is a direct transfer. So in conclusion, we could see that the net subfilter energy transfer rate is dissipative in the upper troposphere and backscattering in the lower stratosphere. So the net subfilter energy transfer rate is the sum of large amount of dissipation and backscatter in both upper troposphere and lower stratosphere. And then the result from the box filter and Gaussian is almost identical, and the color, and it's just significantly bigger with the spectral color filter. And then we could see that there is like direct energy transfer in the upper troposphere and inverse energy transfer in the lower stratosphere. And for that, this is the end of my presentation. Thank you.
Great. Thanks, Donald. You have time for a quick question?
Yeah, I think so.
I don't see any questions on the event Mobi, so maybe I'll just ask. So if backscatter is so important, how can that be incorporated into eddy viscosity models?
I mean, one thing that I'm currently doing right now is I try to add a stochastic component into the eddy viscosity so that it could generate a kind of like, what's that called, like a backscatter in the eddy viscosity. yeah, that's what I'm trying to do right now.
Super. Okay, thanks. Okay, so thanks a lot. Maybe just one quick reminder for the audience. If you want to ask questions, you can put them in the Q&A box on the event Mobi page. Okay, so our next speaker is Rosalie Cormier, who is going to talk about climate change and the changing dynamics of the Beaufort Gyre.
Awesome, thank you. Is the screen share working?
Not yet.
Okay.
It says that it started screen sharing. Double click to enter full screen mode. But I don't see your talk yet.
Try again.
Oh, okay. I see it
Good.
now.
Okay,
Yeah, good.
sorry.
Okay.
All right, so my name is Rosalie Cormier. I'm a graduate student at the University of Waterloo, and the work that I'm doing towards my thesis is on modeling baroclinic instability in the Beaufort Gyre. So I'll start by talking about the dynamics of the Beaufort Gyre, including baroclinic instability and the recent history of the Beaufort Gyre. So for those who don't know, the Beaufort Gyre is a major anticyclonic region of circulation in the Canada Basin of the Arctic. It's a wind-driven gyre, and it's very important to Arctic climate for several reasons, and I'll highlight a couple here. So the first is that the mixed layer of the Beaufort Gyre constitutes the largest reservoir of freshwater in the Arctic Ocean, and this comes from a variety of sources, but principally from river and groundwater drainage. The second feature of the Beaufort Gyre that's very important to Arctic climate is that below the mixed layer and really below the gyre circulation itself, the Pacific summer water layer of this region stores large amounts of heat. So as you can see in the figure on the left here at about 400, 500 meters depth, the potential temperature of that water is very warm. Because it's overlaid by a large layer of freshwater, the warm water tends to stay at depth. That said, the Beaufort Gyre is in geostrophic balance at leading order, and this is a baroclinically unstable state. So one implication of that baroclinic instability is that we tend to have that strong stratification. The wind forcing by the Beaufort High at the sea surface causes a shear in the velocity profile. In particular, as you would expect, there tend to be very fast currents at the surface of the gyre, and that decays to a more quiescent profile at depth. The wind stress doesn't need to be very strong to create small perturbations from a geostrophic state. And since the gyre is baroclinically unstable, these perturbations can and do grow into large baroclinic eddies on length scales of about 10 kilometers or sometimes larger that serve to mix the gyre and weaken its stratification. So when the gyre is in a state of weakened stratification, this is more amenable to vertical transport. And so we do see more vertical mixing and some warm water at depth being transported upwards. So some of the questions that are motivating my research are: how does variability in the Beaufort High wind system affect baroclinic instability in the Beaufort Gyre? And how impactful is the mixing by the baroclinic eddies on the stratification of the gyre? So I'll step back a little bit now and talk about our understanding of the recent history of the Beaufort Gyre using ECHO, estimating the circulation and climate of the ocean. ECHO is NASA's adjoint model for ocean reanalysis. It obtains data from a variety of in situ and satellite instruments. I've named here Argo floats and the Jason-3 payload, but ECHO draws data from a really diverse array of sources, I think upwards of 50 different sources. It then assimilates these observations using the MIT GCM framework, and it ultimately outputs daily estimates of all the fields needed to evolve the global ocean from 1992 to the end of 2017. A couple of nice features of the ECHO model are that it imposes realistic dynamic and thermodynamic constraints on this assimilation. So every output, every estimate is a physically realizable oceanic state. And also the ECHO model output is successful in reproducing the original observational data to the required accuracy, which is great. The figure on the bottom left here shows the average grid spacing of the grid on which ECHO specifies its fields. So in the center is the Arctic Ocean. You can see that there's an average grid spacing of about 40 to 50 kilometers in that region, which includes the Beaufort Gyre. So this is an animation of a couple of the fields the ECHO outputs, the density anomaly in color and the horizontal velocity shown as vectors. And this is animated. These are the annual averages animated over the entire 26-year period the ECHO spans. So a couple features I'd like to highlight are, one, the color is changing over this time span. So it starts being near zero and becomes quite negative by the 2010s. This is consistent with Arctic observations. This corresponds to general freshening of the water and potentially also warming of the water. And secondly, the horizontal velocity is increasing. So we do, for every year, have that anticyclonic circulation pattern, but in the late noughts and the early 2010s, the strength of that circulation increases dramatically. Another profile I'd like to show here is this animation of the vertical potential temperature flux in the Beaufort Gyre region. So this is just the integral over the water column of the vertical velocity times the potential temperature. So you'll see here not a lot of activity in the 1990s, early 2000s, but again, past about 2007, 2008, we start to see these large patches of dark red, which correspond to a net upward temperature flux. So I'll talk now about the work that we're starting and continuing on numerical simulation of a model of the Beaufort Gyre. So I recall here the motivating questions I posed before. How does variability in the wind system affect baroclinic instability in the ocean? And how impactful is the mixing by baroclinic eddies on the gyre stratification? So ECHO model data, while insightful, cannot answer these questions sufficiently for a few reasons. First, ECHO is quite coarsely resolved. You'll recall in the Arctic Ocean, which is the part of the ocean that has the best resolution in the ECHO model, the grid spacing is still about 40 to 50 kilometers, whereas some of the baroclinic eddies are on scales of 10 kilometers or so. Additionally, ECHO outputs estimates only once a day, so the temporal resolution is quite coarse for our purposes as well. Additionally, the goal of the ECHO project was to produce a realistic hindcast of the ocean, which it succeeds in, but it's limited by that scope. And so we can't use the ECHO output to isolate for the effects of baroclinic instability in a particular region. So our plan now is informed by what we see in the ECHO data to use a simulation of an idealized model of the Beaufort Gyre to determine more precisely what the specific relationships are between baroclinic instability and the stratification of the gyre. So we construct our model assuming just a geostrophic background state. We have a hydrostatic background pressure, and we superimpose a Gaussian gyre pressure on top of that. I justify here our choice to use a geostrophic background state using representative velocity and length scales that are typical in the upper Beaufort Gyre. The Rossby number in that region tends to be a little bit below unity, but it's close enough for our idealized model. So this is our background state that we construct, and the velocity profile is shown in the figure on the left. Not very exciting. We set up our simulations using the Oceananigans Julia library, which provides a finite volume method for solving fluid dynamical simulations. And then when we initialize this geostrophic background state, we assume geostrophy in all fields, but to our buoyancy field, we add a small random perturbation. And then that's it. We allow the gyre to evolve without external forcing. And because that geostrophic state is inherently baroclinically unstable, certain modes within that random perturbation will be inclined to grow, and we see baroclinic eddies start to form. So unfortunately, we're pretty early in the stages of executing these simulations, but I did want to share one example of the baroclinic eddies that are observed in our simulation output. So this is the buoyancy field at 125 meters depth in our simulated gyre, and you'll see it takes a couple days of simulation time, but eventually here around day 3, day 4, we start to see some of those more coherent wave-like structures emerge, and those are characteristic of baroclinic eddy mixing. So the analysis portion of this project will focus on looking at trends in the buoyancy field, and also in the buoyancy perturbation field. So looking at how strongly the gyre deviates from geostrophy in the long term. Next steps in setting up our model are to gradually add details to make the gyre more realistic, more similar to the real Beaufort Gyre. So of course, first we need to impose wind forcing, and this will be instated as a boundary condition on the upper surface of our simulation domain. When we impose wind forcing, we need to incorporate the seasonal trends in the Beaufort High, the weakening and strengthening with the seasons. And then we also would like to incorporate the Arctic Oscillation, which affects the Beaufort High on a longer time scale with a period of about 10 years. We'd also like to set up a more realistic stratification within the gyre to reflect what we see in reality. And then eventually also add an ice cover, which we'll implement just as a damping term on that wind forcing boundary condition, because that is the primary effect of the sea ice cover in the gyre. Eventually, we'll be comparing the simulation output to notable features in the ECHO model data, and I hope to have more details on that to share with you at a future conference. So just to provide a quick summary, the Beaufort Gyre is very important to the Arctic Ocean because it stores large quantities of fresh water and heat, and of course also large quantities of potential energy because of its baroclinic instability. The mixing by the eddies in the gyre allows for more vertical transport to occur and allows for some of that heat to be released to the surface. ECHO provides a realistic picture of the Beaufort Gyre's historical evolution, but it's constrained to large length and time scales, which means that it tends to smooth out the baroclinic eddies and other mesoscale processes. Numerical simulation is the way that we're hoping to be able to empirically study causal relationships between the physical variables of wind forcing, baroclinic instability, and stratification at the resolutions necessary. And that's it. I hope I'm early. Happy to take any questions.
Yeah, I skipped the 2-minute warning because
okay.
I could tell you were wrapping up, so it was great. Yeah, we have time for a couple questions. I'll just check the. So if anybody has any questions, you can type them in on the Event Mobi Q&A box. So maybe while people in the audience are thinking about that, I will ask a question. So you mentioned more realistic boundary conditions in future work, but what were the boundary conditions that you used in the simulation you showed? And I'm sorry if you mentioned it, I might have missed it. But
no, I didn't mention. Yeah, so it's pretty simple right now. You can see that the gyre is quite small within the domain we're using. So the lateral boundary conditions don't affect the dynamics much at this point. So right now, the lateral conditions are periodic, but it doesn't seem to be influencing the gyre. And then in the vertical, we've got no flux, free slip, both at the top and the bottom.
And how did you choose the initial conditions, like the shape of the gyre?
Just assuming geostrophic balance, and the shape of the gyre was informed by the pressure profiles that we saw in the ECHO data. It tends to be sort of Gaussian.
Great. Yeah. Check. Oh, shoot, I actually see a question, and now I'm not sure if it was. There's a question about vertical heat transfer, but I worry that might have been the talk before you. So I'm sorry if I missed it earlier. Okay. Okay, thanks a lot.
Thank you.
Okay, so we have about a minute or so, but that's good because our next speaker, Will Perry, maybe we can just quickly check that your screen sharing works.
Can you hear me?
Yeah, I can hear you.
Okay, I'm going to try to share my screen.
Perfect.
Oh, how about that? Can you see that?
Yeah, I see your whole PowerPoint window. You want to if you put it in presentation mode so it fills the screen. Perfect.
Like that.
Yeah, that's great. Okay, so I'll give you a minute, a 2-minute warning when you're at the 10-minute mark, just so we allow a few minutes for questions at the end.
Okay.
So thank you. So yeah, our next talk is by Will Perry, and he's going to talk about is the winter Beaufort High weakening under warming climate scenarios. So go ahead.
Thank you very much. And I want to thank you for this chance to make this presentation. To begin with, I want to acknowledge my co-authors, Mingfeng John and Zhenshan Long. So Mingfeng conceived the study, designed the study, and did most of the work, and Zhenshan provided critical comments and reviews along the way, and I would say myself, I was the cheerleader and I tried to help and stay out of the way. I guess you could say that. So let's go ahead. Here's an outline of what I'm going to present. Give a motivation, discuss the data that we'll use, present something about the decreasing sea level pressure with Beaufort High, and show some changes in Beaufort High vorticity and associated changes in upper level North American ridge. And lastly, give a summary. And at the bottom, there's a manuscript we've prepared and submitted to GRL. So we're waiting to see what the reviewers think of that. Okay, so previous talk was very motivational. We talked about the Beaufort Gyre. This is talking about the Beaufort High. Beaufort High is a dominant atmospheric circulation system, and it drives the Beaufort Gyre and anticyclonic sea ice motion. Variations in the Beaufort High can have a significant impact on the sea ice and the ocean circulation. So Beaufort High is important. It's still an open scientific question as to how the Beaufort High will change in a warming climate. So in terms of data, the basis of our study will be outputs from 25 models from CMOS under 3 scenarios, the shared socioeconomical pathways, SSPs. We'll look at historical experiments and future projections. So historical is mid-20th century to 2014, and future is 2015 to the end of the century. ERA5 will be used to evaluate model performance, and linear transit significance levels are for average winter data, December, January, February. So here's an example of the data showing sea level pressure decreases in the Arctic. So change in sea level pressure with MM mixed model mean. And what we see here is that the index of Beaufort High. It has a robust decreasing trend with SSP 5-8.5 and 4.5, a reduction of 5 hectopascal, 2 hectopascal by end of the century. And this plot shows the SSP decreases in the Arctic. I got ahead of myself. It's change in sea level pressure with the mixed model mean of 8.5. And so that's the difference. And what we see is decreases over the Arctic basin under 8.5, 4.5, by the end of the century up to 5 hectopascal for the mixed model mean. Here's time series of, not time series, it's a correlation plot showing decreasing trends of Beaufort high sea level pressure associated with background sea level pressure over the Arctic. Average sea level pressure of the Arctic has similar trend as Beaufort High index for the 3 SSPEs. The change in sea level pressure, which is the y-axis, appears to correlate well with changes in the air temperature at the surface. Correlation is minus 0.7 during the last 2 decades of the 21st century. What about vorticity? In the present climate, a stronger Beaufort high usually is related to higher sea level pressure and anticyclonic vorticity. But in the warming scenarios, changes in Beaufort high, anticyclonic vorticity under warming scenarios, changes in Beaufort high are related to anticyclonic vorticity under warming scenarios in 4.5 to 2.5. Those are weak compared to 8.5. Beaufort high becomes significantly intensified under 8.5. And so here's on the right plot, here's a difference plot of 8.5 minus historical, showing you changes in the Beaufort high. Okay, so now looking at Beaufort high index, vorticity index of Beaufort high as a function of time. So historical data on the left side compared with the RA5, and then for the right 2/3 of the plot shows you the future scenarios for the CMAP 6 8.5 plots. And the bottom two curves, the bottom two time series is comparison of 2.45 and 1.26. So the results are not quite as dramatic. For 8.5 and 4.5, the results are a robust decreasing linear trend at the 95 point significance level, and the slope is rather small. I won't give you the numbers, it's rather tiny. What about the changes in the ridge over the Western Arctic? So you can see the ridge in the plot in the left panel, and the Beaufort high vorticity is linked to this ridge in the 500 hectopascal of the Western North America. Strong Beaufort high is usually linked to east of the ridge at 500 hectopascal. Anomalous positive geopotential height over the Beaufort high region is a polar extension of the amplified West North Atlantic ridge, and changes in the Beaufort high are well correlated with changes in this 500 hectopascal correlation. We can see that in the right panel, the correlation of 0.72 for scenario 8.5. It's not quite as high correlation for the other two scenarios, and that's for the last two decades of the 21st century. And so looking at the enhanced ridge over the Western Arctic, this plot shows time series for the scenario 8.5 of 500 hectopascal vorticity associated with ridge over the Western Arctic, and it shows a decreasing trend, so that's larger anticyclonic vorticity. And now, getting near the end of the presentation, the enhanced ridge over the Western Arctic. Under scenario 8.5, the CMAP 6 climate models give the northeast shift of the East Asian trough, and you can see that in the dipole in the plots for historical data 8.5, and the difference showing you the shift in the East Asian trough, if you can see the map, over the subtropical Pacific. And so it's positive changes in the 500 hectopascal and negative changes over the mid-latitude Pacific from the mixed model mean. Northward shifted and intensified East Asian trough pushes the West North American ridge to the northeast and increases the associated height gradients over the Western Arctic. So that brings us to the conclusions of the findings of what we've investigated here. First of all, I'll remind you of the question. The question was, is the Beaufort high weakening under warming climate change, or is it intensifying? And so what we looked at was the Beaufort high index defined by sea level trends, and we find that it decreases over the 21st century with the warming scenarios 8.5, 4.5, but the decreasing trends, the Beaufort high sea level pressure are associated with decreases in the background sea level pressure over the Arctic basin. So perhaps that's not a surprise. But on the other hand, the intensity of the Beaufort high, defined by vorticity, is tending to increase in the 21st century under the 8.5 scenario. But we find no robust change for the other two scenarios. So that's kind of going in the other direction. So we kind of leave this presentation with the idea that it's necessary to consider the dynamical intensity of the Beaufort High, such as vorticity, rather than merely the thermodynamic indicators, which would be sea level pressure in studies of Arctic climate change. And that's all that I have to present. So I'll stop here and welcome any questions.
Okay, great. Thank you. And I apologize for missing a question on the last talk. Yeah, so does seem to be a question for you, Will, online. I can read it. It says, for lower pressure tendency of the Beaufort High, does it impact the storm track for the Northern Pacific or even the North Atlantic storm track wrapping in from Greenland?
So just to repeat that, make sure I got it straight. You're asking, decreasing sea level pressure, does it impact these storm tracks?
Yeah.
North Pacific and around Greenland. Oh, so we have another study about Arctic cyclones and the effects of storm tracks. So we don't really get into that here. The other manuscript is looking at the composite Arctic basin. I don't remember that we got into the sea level pressure changes in Beaufort Sea as a sort of trigger or as a dominant mechanism for these changes in storm tracks in the other parts of the basin in terms of future scenarios. I would say that probably the dominant effect would be changes in sea level, changes in sea ice. So if you think that the future Arctic could have summertime largely open water, then the storm tracks in the summer are going to be quite a lot different from now, whereas at least now we still have a lot of ice in the Arctic. In the wintertime, the Arctic is going to still have lots of ice throughout the total Arctic. So I don't, I'm just trying to remember the other manuscript. I don't think there's a dominant change in the storm tracks. I'm sure my co-authors will correct me if I got that wrong, but I don't see the Beaufort High sea level pressure as a major trigger in changes in these storm tracks. It is part of the composite system, and changes in the wintertime storm tracks will be manifest in the other factors that are going on. I hope I didn't ramble on too much there.
No, that's great. Yeah, thank you. Just quickly check online to see if there's any additional questions. But I'm not seeing any, and I was going to ask you about just implications of the changes you're seeing, but I think you touched on that nicely in your answer to the last question. So thank you. Yeah. Thanks.
So I guess I can stop sharing and
Yeah,
mute myself.
perfect. Okay, so our next speaker is Victorien de Meyer. Do you want to share your screen?
Yeah, sure. Yeah, do you see my screen?
Yep, yeah, perfect. It's
Okay,
in
cool.
full screen mode now. So
Yeah.
Right, so our next talk is analyzing North American cyclones in CMIP 6 models through an Eulerian approach. So
Okay, thank you. Thank you very much. Thank you for having me. So yeah, my name is Victorien. I'm a postdoc at UQAM University in Montreal, and it's work we are conducting currently with Alejandro Di Luca and Philippe Gachon about the analysis of the North American cyclone, as we'll see through my presentation. So the purpose of what we do here is to actually, at a later stage, study extreme precipitation and strong wind events in regional climate model simulations. But to do so, we use dynamical downscaling, which consists in using GCM's data as boundary conditions for regional model to allow for higher resolution simulations that might be more suited to study sub-daily extreme. So this study here, we are aiming with that study to evaluate GCMs from CMIP6 based on their ability to reproduce the large-scale synoptic atmospheric conditions that are favorable to extreme events of precipitation and wind in mid-latitudes. And so we consider both dynamical and thermodynamical fields because we think that are at the large scale the important fields when it comes that can lead to extreme events of precipitation and wind. So we use both mean sea level pressure and near surface humidity. Also, we employ, as we will see later, sorry, an Eulerian approach to identify the most intense extratropical cyclone in North America. So the fields of pressure and humidity we use are coming from 27 different CMIP6 models that are listed here on the right side of the presentation of the slide. We use a period of 35 years from 1980 to 2014, coming from the historical experiment of CMIP6. And those model data are compared to the ERA 5 fields of the same period, 1980 to 2014. And this ERA 5 is considered here in our study as the reference, and it will be helpful to estimate the errors of the model. So each time I'm going to talk about errors here of the models, it's compared to ERA 5 fields. We also decided to include high resolution regional climate model to the study, the CRCM6 that is developed here at UCAM. The simulation is driven by ERA 5 at the boundaries, and it will allow us to evaluate the added value of the high resolution. Although all data have been regraded on a common 1.5 degree grid every 6 hours. So the Eulerian approach we use consists in identifying the strongest pressure anomaly on each grid point for each year. It means that across all North America, for every grid point, we have the 35 strongest storms, one per year. We only keep in the analysis the 7 strongest storms out of the 35, and we then extract the 6 days time series around the minimum. And that's what is shown here on the plot on the right side. You have the average of the 7 strongest storms on the Montreal grid point here as an example of both ERA 5 for the black line and for a random model here, the CRCM6 for the red thick line. We introduced then a linear fit to the time series, as you can see now on the plot with the dotted lines. That linear fit is actually the sum of 3 different parameters that have all a physical meaning and will be very helpful to study more in depth the error we get. For example, we have C for the center. It's actually just the value at the time 0 at the strongest anomaly, the pressure anomaly. We have the depth, which is the rate of deepening of the storm, so pretty much the slope of the dotted line. And we have also A for the asymmetry, which tells us about how symmetrical is the storm compared to the line where X equals 0. We use several error metrics. In that presentation, I'll use 2, the mean absolute error, or MAE, between ERA 5 and the model's time series. It's pretty much only the absolute gap between the black and the red curves across the time series. And I'm gonna also use the bias of the 3 parameters between ERA 5 and the models. We do the same thing for the near surface humidity with a little difference is that we're not looking for the strongest near surface humidity anomalies, but just the near surface humidity corresponding to the storms that we identified first with the strongest pressure anomaly. And we apply the same linear fit also to the humidity. So when looking at the mean absolute error, so the MAE of the model ensemble mean, so the 28 model that we use over North America, the domain that we use here, that's what you can see on the upper right corner of that slide. You can see that this error, the MAE, is pretty low across the whole domain. We have a domain average across between the 28 models of 3.8 hectopascal, which is quite low. Although we have some regions, for example, in the center of the USA here, you can see also in the Atlantic Ocean, especially sorry, in the north of the Atlantic Ocean, we have higher errors of the model compared to ERA 5, up to 10 hectopascal of error. And looking at the MAE this time calculated with the linear fit. So it's actually the relative error between the MAE and the one calculated with the linear fit here. So that plot actually tells us is the linear fit a valid approximation of our time series, okay? You can see here that we have pretty strong value around the tropics, especially in the Caribbean Sea. It means that we have to be extra careful using that linear fit in that region. Otherwise, on the whole domain, we have a pretty low relative error between the two MAE, meaning that the linear fit, when it comes to studying the error between the models and ERA 5, is actually a good fit. Now, not looking at the model ensemble mean, but at the domain average of all the 28 models that we use. That's what you have here on that scatter plot. So on the x-axis, it's just the pressure MAE, and on the right axis, the humidity MAE now. The closer you are to the origin, and the lower it is the error. You can see here a cluster of model here that is gathered around with an average error, I would say, between 3.75 and 4 hectopascal for the pressure anomaly, and between around 1 gram per kilogram of humidity. We have, though, some outliers on the good side. We have some like 3 models that seems to perform better than the others when it comes to that framework. For example, you have the 2 models from GFTL that we use with a low error both in humidity and pressure anomaly. And we have also the 11th, that is the RCM simulation we use, the CRCM6, which is not a very surprising result since it's a simulation that has been driven by ERA 5 at the boundary. Although it might be the added value of the high resolution. On the wrong side of the plot, I would say, we have outliers also with CAN ESM5, which is pretty bad, or I mean, the error when it comes to humidity is pretty high here. And you can see also the BCC CSM2 or the GSE2 are also have a high error when it comes to the pressure anomaly. So if we take a more in-depth look through the 3 parameters of the linear fit and their spatial distribution, it's what we can see here on those maps. So the first column is actually the raw value of the 3 parameters in ERA 5, and the right column here is just the bias of the model minus ERA 5. What we can see for the center parameter, which is like the lowest value of the pressure, or the highest value of the pressure anomaly, I should say, you can see that in the tropics, that the model struggle to reach the high ERA 5 pressure anomaly values that we have in that region. And we see the opposite when it comes to the northwest of Canada, where the storms are stronger in the model than in ERA 5. And interestingly, when looking at the depth parameters, so the rate of deepening of the storm, we have opposite bias to the center, with negative bias here in the tropics, for example, and positive bias in Northwest America, but it's the same across the whole domain. You can see here for the asymmetry parameter that in ERA 5 data, you have quite an interesting result here. You can see that on the northeast of Canada, the storms are quite asymmetrical here. You can see with the blue grid boxes. And looking at the bias of the model here in that region, you can see that the model, they struggle to accurately represent the asymmetric storms in that region, with both a positive bias in the north, and when you get inland, negative bias. So we will focus on 2 regions later and to see a little bit more about that. So the first focus we do is on the Atlantic North. In that domain here, you can see on the map, it was a region where we had opposite bias when it came to the center and to the depth. And here you can see on those 2 scatter plots here, it's not exactly the same as before, because now it's for the center and the depth. So it's for 2 parameters, and it's also the bias. what we can see here is that most of the models here, when it comes to the center, have negative bias here because they are below the line where y equals 0, okay? And it's actually, when it comes to the pressure, the opposite in here, where all the depth anomaly is actually positive in here. So it means the two parameters are quite compensating when it comes to the pressure anomaly. And it's actually the same behavior when it comes to the humidity, where the storms are actually not humid enough because they are right side of the line where x equals 0. And so they're not humid enough, and the rate of deepening of the near surface humidity is too high. So it means that taking, for example, a random model here, I decided to take the Meyer ES2L on a random grid point of that region. It's one of the models that shows one of the strongest bias when it comes to the pressure. So you can see it's number 20, and it has a pretty high anomaly. And pretty high bias, sorry. And you can see on that random grid point that the model actually start with the same background pressure before and after the storm as the grid point, but the pressure anomaly is pretty high when it comes to ERA 5, but pretty low when it comes to the model. So it just showcased that the fact that the two parameters are compensating each other, it comes from the fact that the models in that region struggle to reach the very high, strongest anomaly, the very high pressure anomaly of ERA 5 in that region. And looking now into the Quebec region where we had those asymmetric storm, here I show the 3 parameters this time, and what we can see on the 3 parameters, with the asymmetric one being the most important one we will see. We can see that for the pressure anomaly on the x-axis, all the model seems to be pretty evenly distributed around the origin, okay? It's the same when it comes to the depth parameters, but for the asymmetric term, you can see that all the models are on the left side of the line where x equals 0. It means that for all the model, they have a high bias and negative bias for the asymmetry parameters. And same, taking representative model with an average bias, here the CNRM ESM2 on the Montreal grid point here, we can show that behavior more precisely. We can see that both for ERA 5 and the CNRM for the model, the anomaly pressure is almost the same, so we don't have any bias for the center parameter. We don't have any bias, although for the depth parameters, we can see the rate of deepening of the 2 dotted lines are pretty much the same, but we can see that those storms are way more asymmetric in the model than they are in ERA 5. The pressure rises just back up too slowly after reaching its minimum in the model here, and it's what we can fairly think about all the other models, and that's we think and the behaviors of most of the model in that regions. So to conclude, that methodology that we use aims to identify the GCMs that can accurately simulate the synoptic conditions that are associated with the storms, and that can likely result in extreme precipitation or strong winds in the mid-latitudes. The Eulerian method we use is pretty simple and uses both dynamical and thermodynamical variables. And we derived a single error matrix that combines information about the evolution of the pressure and the humidity with a physical meaning to the error. And we show that in this framework, some GCMs are able to outperform other models, and also that the CRCM6 model almost always show the lowest error, potentially thanks to the highest resolution of that RCM. Thank you very much.
Great, thank you. Let me just have a quick check. If there's any questions, you can type them in online. We have a minute or so for questions. Maybe I'll ask a quick one. So a lot of the models seem to have similar error. I think your last slide, you showed that most of them had negative bias for asymmetry.
Yes.
What is the mechanism for that? What are the models all doing wrong? What do you think?
I mean, that's a good question. And that's what we're trying to understand now. It's the next step of the study, I would say. It's pretty surprising because I was expecting when I saw that first that it was actually ERA 5 that has a symmetrical storm and I mean, on their Montreal grid point at least. But yeah, most of the model here, and I've seen that plot for many models, it's actually the models that struggle to have the pressure that rises back up at the same rate after the storms as hit the grid point. I don't really know why. It's like we are discussing about it right now with the co-author, and I think I'll have a little bit more knowledge about it that in the next few weeks.
Okay. Great. Great. Thanks a lot. I actually see that there's some questions in the chat window. Gosh, sorry. But I don't think any of them are for you. So apologies for missing those. Okay, thanks a lot. Okay, and yep, so we have our final speaker of the session, I think is here, Yoandy Alonso. Do you want to unmute and share your screen, please?
Yeah, okay, can you hear me?
Yep, yeah, we can hear you.
Okay, yeah, good afternoon.
Can you share your screen?
Yeah, okay. Okay. Okay, can you,
Yep.
okay,
Yep.
okay.
Perfect. Okay, yep, so
Good
go ahead.
afternoon. Okay, good afternoon, everyone. My name is Yoandy Alonso. I am a postdoc at the Université de Montréal. My supervisor is Jess King, and also in this work we have a collaboration of Hélène Coté and Diana Music from Ouranos. So today we're going to talk about a little bit about the jet streams. For do that, well, you know that we know that the jet streams are fast flowing narrow air currents in the Earth's atmosphere that plays a key role in atmospheric circulation, affecting the weather and the regional climate, and also in global scales. The extreme weather events, including heat waves, cold snaps, and altered ocean currents, can be linked to the jet stream as well. So, to detect this phenomenon, we use the methodology that is based on the maximum wind speed and the minimum wind speed in a certain latitude. And we could detect the jet stream. For example, in this figure, this is the wind speed at 250 millibar from the ensemble of the CM5 Uranus. We can see that the field is this yellow area is the greatest area of the maximum wind speed, and the hatched lines is the jet stream core detection by this methodology. So in this research, we analyze an ensemble with the 4 global climate models, and also 4 CM5 driven by the same GCMs. And also we compare these RCMs with the reanalysis data, and in 2 climate feature scenarios, RCP 4.5 and RCP 8.5. The baseline, the historical period, is from 1980 until 2010, and for the future period is 2071 until 2010. The daily mean values are used in all these experiments. So, how well does the ensemble of the CM5 Uranus represent the jet stream? So, for answer this question, we have the left panel, the CM5 in the different seasons of the year. This is the frequency distribution of the jet centers. And the middle column is the era 5. So we can see the third column is the jet center's the bias. So the difference between the era 5 and the ensemble of the CM5, and we can see there is not too much difference between them. So the representation is reasonable well. It's important to notice here that the red lines represents the jet centers for the model, and the black line for the reanalysis data. So the right panel is the same, but in this case with the wind speed for the entire domain. We can see that the representation of the jet stream is not bad at all compared with the reanalysis. So this going a little bit deeper in the analysis, we can see we construct violent plots with the position of the jet stream in the top panels for the models in the historical period and for the era 5 in the same historical period. And we can see that the representation in the different seasons is well correlated, as well for the wind speed, the bottom panels. So what are the future projections for the jet stream? First of all, we have the left panel, the RCP 4.5 scenario. On the left, the right side, we have the RCP 8.5. For the RCP 4.5, we have the historical period, future period for the same RCM ensemble at 250 millibars. We can see that during winter is a little bit shift in the north, in the west coast of Canada, and during the summer and autumn months we have a shift northward in this scenario. When we move to the 8.5, it's more or less the same situation, except that during spring we have a more pronounced shift southward, and during summer and fall, this shift to the north is more pronounced, with an increase of more than 30% in this period of the future. Like the past figures, the red line in this case means that the position for the historical period of the jet stream, and the black line, the position in the future. So for the wind speed, the analysis is similar. The left panel is for RCP 4.5, the right panel is RCP 8.5. First column, historical period, the middle is the future projection, and the third column is the difference between both historical and future. And we can see that during the fall, this a shift to the south in the decreasing the tendencies, the wind speed in the south is to decrease. This is the blue color. And for the RCP 8.5, we see more or less the same situation. The decreasing the wind speed is a little bit greater in this case. And it's important to notice that for summer, the decreasing the jet stream wind speed values is so notable that in some points wind speed values over 30 meters%, which is the blue color, tend to disappear. So for the global, for the ensemble of the same drivers model for this RCM5, we have the fourth members that we make with that an ensemble with these globals. So for the RCP 4.5 and also for the RCP 8.5, we have more or less the same conclusions, the same movements in the jet stream to the south during spring, to the north in summer, and fall in both scenarios, and more pronounced in the RCP 8.5, with movement values, the difference greater than 30% in the RCP 8.5 scenario. For wind speed, due to the global climate model has these models have a less resolution. The fields of the wind speed are smoother compared with the RCM with the regional climate models. We can see that in this case, except for winter, the wind speed it's not over the 30 meters per second in this case, but we can see that the decreasing areas of wind speeds in this 250 millibars still being the same that the RCM5. So, like a conclusion, we can see that from CM5 simulation driven by these 4 or CM5 GCMs, first of all, the mean position of the jet stream tends to shift northward up to 3 degrees, more or less, during the summer and fall months, and southward during the other seasons. And notably, this behavior is more pronounced in the RCP 8.5 scenario for the 2070 until 2100 period. The intensity of the jet stream measured by maximum wind speed shows an increase during the winter and a decrease during the summer in the future projections. And it is important to notice that the RCM5 at 250 millibars is strongly constrained by its driving model. So thank you very much.
Okay, thank you. Yeah, we have time for some questions, and I apologize for missing questions in the chat window. There's a lot of windows. So let me just see if there are any questions for you online. If not, people are welcome to type one in. I'll check both boxes. I don't see any. I mean, maybe I will just ask you, what is the next step in this work?
Yeah, this is the preliminary work. The next step would be do the same methodology, but with much more members. Well, in this case, we only analyze 4 members of GCMs and 4 members of the GCMs. We are working with much more members, and also with different heights. We are analyzing 300 millibars and also 200 millibars to see if this shift is due to the movement of the jet stream in the vertical, or just a weakening in the intensity of the jet stream or not.
Yeah, thank you. And there's a couple other questions. I will just read them. They're from the Q&A window. So one of them is about blocking. What do these changes in the jet stream mean for atmospheric blocking events in the future?
Yeah, that is a very, very good question. If the jet stream in the future projections moved in the northward, it will affect a lot would affect the principal the pathway of the storms, for example. So I think this phenomena is it has a very, very good it has a real impact in the other rest of the meteorological events. So we need to go a little bit further in analysis in order to study the real consequences that could produce, for example, in these winter storms and heat events, etc.
Okay. And just one last quick question from the Q&A window. Are there any improvements of the regional models regarding the 250 millibar maximum speed, since it is a large scale variable?
I'm sorry, could you repeat the question, please?
It's regarding if you look at the 250 millibar maximum speed of the jet stream, do the models do any better?
No, no. This is 250 millibar is not about the wind speed. This 250 millibar is the height, is the layer of the atmosphere that we are analyzing this model outputs.
Okay.
Yeah.
Okay, that brings us to the end of our scheduled time. So maybe I'll just so you Yoandy, you can stop sharing, and I figured out how to clap. So maybe we'll just say thank you once again to all the speakers today. We had 6 great
Thank
talks,
you very much.
and I hope yeah, you enjoy the rest of the conference this week. Thanks very much for coming.
Thanks very much, everyone, and thanks very
Thank you
much,
very
Michael,
much.
for sharing.
Great, thanks.
Bye.